Okay, good morning, everyone. I'm really excited to be here. Getting to see some of the talks already. It's really exciting to see how RISC-V is being used. But I want to give some context for my talk this morning, right? So I started out as an RF engineer, right, designing mixers and filters for RF communication device for spacecraft. Somehow got into doing digital filters and digital designs with FPGAs. Then moved into doing some ASIC work, and finally into doing some algorithm work. So what that turned into was I became a systems engineer. So it's a little different than the hardcore hardware or hardcore software. I did a little bit of everything. And so when I look at things now, I look at it from a system perspective. And so what I wanted to talk about today is some of the challenges in new space and how, open architectures can help solve some of those problems. So there's plenty of different problems in space. So I just chose 6 of them, and one in particular that keeps me up at night, and I'll talk about it very last one. But like one of the things I see is there's so many custom solutions in the kind of market when I say some 35 years ago when I started in this business, and you really couldn't adapt fast enough to the threats even in the market, right? It was really a slow, methodical pace to develop things. It just seemed to take forever. Then there were the system costs that go along with it. There's another one of the challenges, right? Everything costs so much, right? We're not able to leverage common components. The deployment costs, because of all of the software issues that you have as you're doing development, it just takes a long time and costs a tremendous amount. And I think what happens is we get into doing exquisite. I was an engineer at one time too, and we get caught up into doing these exquisite solutions. And I always tell all of our team now that when you say exquisite to me, that's just another word for expensive, right? And I think that kind of says it in and of itself when you talk about these one-off solutions and what it takes to develop, or why it takes so much cost and development time. I think one of the other challenges, and we talked about it already. I saw the information on the using AI in space, and I certainly agree with that. There's a couple of different reasons I think you'll see that as one of the challenges is getting AI on orbit. One of them is just latency. Right? How quickly you can make a decision based on something instead of having to process, terrestrially, you process on orbit, right? I think that's a huge benefit. And then another one of the benefits that I believe with having AI on orbit is just you think about it, position assurance, so you can talk about it as telemetry, just your situational awareness, right? And we all know that, right now, especially if you think of like a LEO orbit, think about how much debris, how much clutter just in general is in that orbit. And I think having AI on orbit that can quickly help you adapt and try to I would say mitigate some of the risks around having all of this debris. That's a huge benefit with having AI on orbit. The next one would be the communications bandwidth, right? And when we start talking about how many sensors are now on space vehicles, and even the communication in between, like the constellations. I talked to a company a few weeks ago. They're talking about having intercommunication on one of their space vehicles may have as many as 8 major data links, serving like as a hub, essentially is the way I like to say it, a hub in their constellation, and had redundancy built into it. That amount of communications bandwidth, that is a real challenge on the new space vehicles. And then you got to think about that transmission down to Earth, right? That again, huge challenge is just the pure bandwidth that we have back and forth between space vehicles and terrestrial vehicles. This next one, it's everywhere now, right? I call it cyber resilience, but everything that we look for as systems designers now. We're always out looking, going, okay, how can I build a system that has an architecture in some way, some fashion, that has cyber resilience that keeps and protects me from cyber events? And I have a really specific example later on in the talk about some work I'm seeing there that's really exciting in its relationship to RISC-V. And this last one is the one that keeps me up at night. If COVID taught any of us anything, it should teach us how fragile our supply chains were. It was one of the most daunting times in my career as an engineering leader, trying to deliver products, whether it was a product for a space vehicle, a product in commercial applications, or even industrial applications. I'm gonna give you guys an example of one of the things that happened. At the time, I was at a company. We were building lots and lots of single board computers for every market you can think of, whether it's space, commercial, industrial. And one of the industrial applications, we were supplying to the largest etching manufacturer in the world, right? They provide etching for TSMC, all of the major foundries that we use. Well, we were needing chips from one of those foundries to design the etching equipment that kept the foundries running. It was a horrible, vicious cycle. And I ended up meeting with the president of TSMC at the time, because I was like, if you don't give us chips, if you don't prioritize this through your vendors, then your foundry is going down. Think about that, right? And it was literally, we were way down the supply chain, but that's how diverse and how intertwined everything is now. And that's just one example of why I think about this, and especially for space. If you really think about with space, the rad hard microelectron, even rad tolerant, forget about rad hard for a second, but even rad tolerant microelectronics, the supply base is very fragile in that. But you have everything into, precision gears, optics, all of the controllers built around them. That's the one thing that keeps me up at night. But I think when you think about this, those are great. Everybody can just lay problems on you, but what do you do to solve some of these? And as a systems engineer, I think about it a little bit different way. And I think you have to start using open architectures to solve those. And that's where I kind of get into the rest of this, is how do you use open architectures, in particular RISC-V, to solve some of those problems? So why open architectures? First, I'd like to get into the tenets, right? Like you can, there's a lot of things that go into what's an open architecture, but for me, I define it kind of very simple, two major components. You have to have interchangeable components or modules. I'll use that term, interchangeable. And then the other one that's really, really important, and it got mentioned earlier this morning, standard protocols. You have to have a communication protocol. It's like communicating with anybody, making sure you can communicate in that language, whether it's, with a computer, it's by voice. That's the most important thing, being able to take the standard protocol for communications and discussions, and then the interchangeable components or modules, so that you can swap between things and have essentially redundancy or backups. So what's that yield? Okay, it yields flexibility. It gives you the ability to have modularization, right? So you can take modules and distribute them all throughout a system and be able to reuse pieces that are underlying, so you keep that core technology. Extensibility. This is a fancy word for saying I can proliferate same modules in multiple places, and now I have a broader knowledge base with them. Velocity, or the rate that you can develop, right? Because you have so many kind of standards that you're working to, not just communication, but also on the actual hardware modules themselves, you get kind of a known base that you can work from. And it just provides multiple solutions. That's the real key. But I think when you have open architectures, it spurs a lot of innovation. You get interoperability, not just between modules at a hardware level or software level, but you get interoperability in the ecosystem between partners. And then what's that really yield? Well, as an executive now, I look at it, it becomes economical for you. You can afford to do more. You can add more feature sets to a system, more feature sets into a space vehicle, and then provide more services to your customer. And I think, we look at open systems architectures. They've been in practice for a long time. You think about it, and I'll go into one of these in detail in just a minute, but computing, networking, telecommunications, and aviation. But I think sometimes when you're looking for innovation or an innovation stack, I think you need to look outside of your industry and see how other people have solved problems. Whether you could look in the financial industry, you could look in automotive, whatever it may be. And I just kind of picked an example, and I went like looking for open architecture examples of where people have taken open architecture, took a kind of a different problem and solved it a different way. And so I used a company called Environmental Systems Research Institute. It's called ISRA. And I love this quote from them. I'm just going to read it from the screen. A science-based geographic approach can help us understand these interconnected problems holistically by integrating all kinds of information. And I took a snapshot. This is from their website. Give them all the credit for it. I really love what they did here. They talk about open standards, open architecture, open source, security and privacy, open architecture, accessibility. And then when I went and looked and did a little bit more research on the company, they're the leading provider. They own 60% of the market for geographic information systems. And they fuse data from everywhere. The data is on space vehicles. They have UAVs. They have old maps that they use. It's phenomenal how they take so many different types and they keep it by having an open architecture, an open framework where they can quickly integrate data. But more importantly, they can integrate new pieces of information and new systems very rapidly by keeping an open architecture. So when you look at open architectures, I wanted to give like one example. I mean, how many people here built their own computers and still do that? I can't be the only nerd that built my own computers. No, okay, good, very good. So I used to love the term plug and play. And you'd have I'm going to use an example. I'll probably tell myself a little bit here, but you take a video board, you would plug it into a motherboard. This was some years ago, but plug a video board into a motherboard, and then I spent the so-called plug and play. I spent 3 weeks debugging a driver for the video card. Right? I mean, okay, I knew everybody's probably been there too, but that kind of open standard, it got me to thinking as I was working through it, hey, this is a really good model that you can use. And I started looking at those models. How do you use that model that was developed in the computing world and take it all the way through systems engineering? And I started doing model-based engineering back in the early 2000s. And I always think back to those early days in computing and how things evolved, right? Like, we talked about protocols, with Ethernet, but think about PCI Express, and before that it was PCI, but USB, all of those standards that come out that were protocols and communication standards. JEDEC. We don't think about it, but think about all the packaging standards that went into place for microelectronics and electronics to build that out. So there was standard packaging where you could have multiple sources and second sources for hardware components at the lowest level. IPC, how the products are used, how you assemble a board even, right? How you solder those products onto circuit cards assemblies. Again, that was a standard space that provided kind of an architecture for how we build things out. Ethernet, I don't want to dwell on that one. We could probably talk about Ethernet and how it's connected things throughout the world now. But one thing about Ethernet that I love, and I put a little graphic in here, is Ethernet has even layers below their overall standards, right? So when you look at OSI and how everything's connected, that's the part that I really love about Ethernet, is it even has a standard within a standard, right? And then you have all the open source software and open source hardware. I picked an example here of a GR765. This is one of the developments. It's a system on a chip that's being developed right here by our Geisler team. It's an octal core system on a chip using RISC-V, as a matter of fact, right? And that open hardware development then going in conjunction with using open software, so open source software like Linux and others, that's how that ecosystem come to play, right? And that's how I felt like open architecture is really accelerating innovation. You can see it in how far we've come, just from my early days of building, computers to what you see now, and the level of integration and how things have been miniaturized, and the power levels of the computing elements are just tremendous now compared to when I started years ago. So all of that's great when you start talking about open architectures. There's problems out here, but I started looking and I wanted to say, okay, how does RISC-V, if I just take the example, how does RISC-V help solve any of those problems, right? And so I looked at the first one, artificial intelligence. Our team, again, here in Geisler, they're working on something called the GR801, the great one. It is a AI-enabled device that will be used for space. And that particular device, you have multiple, in my opinion, it's multiple hardware stacks, it's multiple software stacks, but it's multiple types of computing coming together, right? The heterogeneous computing that's coming together to be able to solve that problem and help put artificial intelligence on orbit. And again, using RISC-V as one of the basis elements for that. Systems costs, right? This one, to me, it's pretty simple. There's more vendors. It's open source. I get the benefit of having more people that can provide me a module or a device that I can use in a system. That's very simple. Development time. I think we talked about this a little bit earlier, right? It really fosters collaboration and innovation. That's what you really look for, right? Is when you have a single system where something's being used, it limits your scope of what you can have. RISC-V with its open source and its open architecture, that's really fostered innovation and collaboration throughout the industry. Seeing how many vendors were up there now was quite amazing to me. I talked about the communications bandwidth. This one's one of the ones that I also am deeply concerned about, being an old RF guy and seeing what it takes to do communication links. I think having that highly efficient, low power processing element that not only commands those data links and defines their usage and efficiency, but can actually do waveform processing in and of itself. That is an incredibly powerful element for comms bandwidths and being able to address that problem. Cyber resilience. I said I had a specific example, and I'm just going to use it a little bit in general terms, but I have knowledge that I know at least 5 different companies that are using RISC cores to offer secure processing elements that can be added into systems. That's just me personally know these people, right? A couple of them are great friends of mine that founded a company to do this very thing, and they're using a RISC-V core to do that. And then the last one that I talked about that really means a lot to me, this supply chain disruption. you saw it on the slides earlier. The supply base is growing tremendously. All the new entrants that are coming into the market, those guys that I was talking about that actually started a business to do, basically, they call it cyber processing. To do that, they started that business. They would have never been able to do this without RISC-V. It would not have happened, right? And but before I close, I wanted to leave you guys with something. I don't know if anybody's ever seen the movie Hackers. It was a movie in I guess the 90s, early 90s. But the movie Hackers, and there's a good article on this, by the way, in a magazine called Wired. But Angelina Jolie was in this movie early in her career. I didn't know who she was at the time. And she's in a group of hackers. These hackers are trying to save the world from some environmental disaster by some supervillain. And her co-hacker there, they're typing away on a machine, and they're talking about how fast the machine was. And then she kind of leans into this, and this is kind of prophetic. This is 30 years ago. She leans into the scene and says, "The RISC architecture is going to change everything." So here we are today. I'm up here talking about how RISC changes all, adapts to all these new space challenges and all the things. And I just happened to read that article coming over here, and I thought, I've got to put this into the speech somehow, some way. I had to put this into the talk. So with that, I'll close and have a few minutes for questions. And I'm keeping you guys from your break, so I'll be brief. But hopefully you guys got to enjoy that and see something from a different perspective of how RISC is helping in the ecosystem.